Thank you everybody for joining us today. So today we will have a UNIST distinguished lecture. So as a part of the Smart Healthcare Research Center series. And today we have Professor STEFAN Hell with us. So it's really an honor to have Professor Hell. So actually, let me just briefly introduce him and tell you about how this webinar will be flowing. So Professor Hell is currently, so I think this is very unique. He holds dual positions as the director in the Max Planck Institute. So he's currently the director for the Max Planck Institute for Biophysical Chemistry. And he's also the director for the Max Planck Institute for Medical Research. And he also holds honorary professor positions at the University of Göttingen and also Heidelberg University. And he, just to briefly describe Professor Hell, he has received so many awards, so I don't think you want to listen to me for a long time discussing all the awards that he has received. So he's receiving awards every year, basically. And so I think I just want to mention about two specific awards that he was awarded in the year 2014. So he was awarded the Copley Prize in Nanoscience. So I think some of you might not be familiar with this award because it's relatively new, but it's a very, very prestigious award that has a $1 million monetary award along with it. And in the same year, he also received the Nobel Prize in Chemistry. So I don't think I have to explain about that. I think everybody would know. And so he revolutionized fluorescence microscopy. So he developed the first method that really worked using far fields. So using conventional lenses, he showed that we can go beyond the diffraction limit in resolution. And I just want to mention one more award that I think is very unique because he received so many awards in basic science, but he also received an award as the Entrepreneur of the Year in 2000 for the Ernst & Young Award with Barrier Instruments, which he actually founded. So he's actually leading basic science and also direct applications, which is really changing how we observe life right now. So he's building the best microscopes in the world. And without further ado, I'd like to pass it on to Professor STEFAN Hell. But before that, just briefly, so today, if you have questions, please use the Q&A spot. So you can type down your questions and then I'll read out the questions at the end of the lecture. Or if you would like to directly discuss the questions with Professor Hell, you can write down video and then I'll just call you and connect you so that you can directly discuss your question with Professor Hell. Okay. So with that, please let's welcome Professor Hell. And again, sorry for the delay. Okay.
Thank you so much. Thank you very much for this very, very kind introduction. I'm very pleased to be able to speak to you today. And I hope you can see my screen now. Can you share my screen?
Could you please share your screen?
Yes. So can you see it now?
Yes.
Yes.
Oh, wonderful. So and can you hear me well? Can you hear me well?
Oh, yes, I can see it.
And I can see your mouse cursor as well.
Very good. Yeah, so thank you very much. Technical problems are normal over such a long distance. I wish I could be in Korea right now, but well, the situation doesn't allow us to do that at this point. Nevertheless, I'm very pleased and also honored to give you a distinguished webinar today. And I'm going to speak about what, as you've heard in the introduction, what really preoccupied me actually for, I would say, 25 years or 30 years, namely the resolution of light microscopy. And some of you may ask, okay, why is light microscopy so important? And the answer is the light microscope was actually the key instrument that really showed humanity that the living world consists of substructure cells as basic units of function and structure, of course, organization. Because with the light microscope, cells were seen for the first time, subcellular organelles such as mitochondria were seen, bacteria were discovered, and so on. But I'm sure you will remember your school days when you were told that the resolution of any light microscope is ultimately limited to about 200 nanometers, meaning about a fifth of a thousandth of a millimeter. And if you want to go smaller than that, if you want to see big details of something that are substantially small, then you have to resort to electron microscopy. Now, electron microscopy, which was invented actually in the mid-20th century in Germany, as a matter of fact, attained a much higher spatial resolution, up to the atomic scale, and got even better and better and better. Now you can even see structure of proteins with electron microscopes. But the problem with electron microscopy is that you can see only that material. So it's not possible to look inside the living cell. You see the molecules in action. You don't see that because it has to be frozen or it has to be arrested. So there is no way to see things in action in the cell. So life at work, so to speak, is not possible to see with the electron microscope. Moreover, nowadays, biologists, molecular biologists, cell biologists, even basic medical scientists want to know, where are certain proteins? Where are certain biomolecules? Are they here or there, or how are they distributed over time, of course? And for electron microscopy, it's very, very hard to single out individual proteins, for example, to see a certain species of proteins very specifically, and then check out where it is. For example, if there is a protein that is upregulated in cancer, it's very, very hard to see specifically that species of protein in the electron microscope. Why? Because it's so hard to highlight it. It's very hard to label it or to make it distinct from the 10,000 of other proteins that are around. Now, fortunately, this is possible in light microscopy, because in light microscopy, there is the option of fluorescent labeling. So it's possible to chemically attach a fluorescent molecule, a molecule that glows if you shine light on it, glows with a different light when you shine light on it. And then if that fluorescent molecule is attached to the protein of interest, then you can highlight it. You don't see the protein of interest, but you see the fluorescence. And then if you see the fluorescence, of course, you know where the protein is. And therefore, light microscopy is so important because it allows you to see proteins very specifically through fluorescence labeling. Therefore, it was clear that if one manages to overcome this resolution barrier of 200 nanometer, then one would really have a big benefit in the life sciences, because one could see specific proteins in much greater detail, and even in live cells in a number of cases, or in many cases. Okay, and therefore it was clear that it would be highly desirable to overcome this barrier, this resolution barrier. But the notion was, throughout the 20th century, that this is impossible. The physics doesn't allow you to do that. And now I'm explaining you why people thought that the physics or the world or nature doesn't allow you to do that, why physics doesn't allow you to get a high resolution. Now, I'm explaining the resolution problem in simple terms. Now, the most important element of a light microscope is the lens. You see, this is the objective lens. And the role of a lens is to focus light down to a point. And light nowadays comes out from a laser, not from a lamp, because no one uses lamps anymore. And then the lens tries to focus the light down to a point, as you can see here from my mouse. And let's assume this is the sample, the black dots, and each of the dots corresponds to a single molecule, for example, a molecule that you want to see. Now, if the lens could focus the light down to a point, to a single molecule, if that was possible, then you could have a resolution that is at the molecular scale. You could have that because you could say, focus the light just on one molecule, and only this molecule will respond with backscattered light or fluorescent light, and then you could see that molecule, you would go to the next, to the next, to the next, and then you could see each of them individually. But that's not possible. Why? Because light propagates as a wave. And because it propagates as a wave, you don't get light to a single point, but you will get a blob of light that has a finite extent. And it's not possible to make that blob smaller than this. So light cannot be focused down to a point. It always has to be a blob like this, a big spot like this. And this spot is about 200 nanometers wide and about 1,000 nanometers along this axis here. So it's not just 200 nanometers in this direction, it's also 1,000 nanometers in that direction. That means that if I'm having here fluorescent molecule falling within this range, of course, they will all emit light, not just this one in the middle, all will emit light. And then, of course, this light will be collected by the lens, yeah, and of course go back to a detector, yeah. But of course, each of the molecule also produces a wave of light, and therefore each of the molecule also produces this big blob of light. And since there are many producing these blobs of light, these blobs will here of fluorescent light will overlap in space, and it's not possible to tell them apart. So no matter what detector we placed in here, could be anything, photomultiplier, could be the eye, of course, could be even the best and fanciest camera that you can buy with the smallest pixel that you can imagine, but the light is still confounded here. It's still just one single blob because it's not possible to know here which of the molecules was actually emitting. So it could be any of them, yeah, and so the signal of all of them is confused. Now, this problem was actually realized by this man, Ernst Abbe, and some other people at the same time towards the end of the 19th century. Actually, in 1873, he made a paper where he said, there will be no way of telling things apart that are closer together than the distance d, given by the wavelengths of light. It's lambda divided by this number. This is the so-called numerical aperture of the objective lens, but forget it. It's just a number like 1 or 2 or at most 3. So in the end, you will never be better than 200 nanometers here in the focal planes. It won't work. And this is Abbe's equation. So this man is called Ernst Abbe. And Abbe's equation is basically found in any textbook of optics, of course, basic physics, but also in textbooks of cell and molecular biology because of the enormous relevance of light microscopy to this field. And it's also found in Jena. This is a university town in Germany where Ernst Abbe lived actually and worked. And he was a big, not only a good scientist, also an industry person who set up a famous optical company that everyone knows. And he actually is commemorated in Jena in his town where he lived with a memorial. And this memorial shows his equation written in stone, basically. And so this equation, which is literally written in stone, was believed to be the end of it. So no way to get a resolution that is better than this distance d. And so when I was a student, I will come back to this about in a few minutes. In the mid 80s, in Heidelberg, in Germany at that time, confocal microscopy came up, and that provided better background suppression and three-dimensional say imaging. Don't worry, it still had a standard resolution. So this is a standard resolution taken, to be honest, with a confocal microscope, but still you can see there is a blur that is due to this phenomenon of diffraction, due to this limit of resolution described by Ernst Abbe. Now, I'm responsible for developing, as you've heard, the introduction of STET microscopy, which was the first viable concept to overcome the resolution barrier that really showed that, no, it's not true. There is physics in this world that allows you to go beyond the diffraction barrier, and you can get sharper pictures than that. This is not the end of it, so it can be done better. And this concept is called STET microscopy. I'm going to explain this in a minute to you. And of course, overcoming this resolution barrier and showing to the world this limit is not written in stone, it's not forever, this can be overcome, has had consequences. And I'm going to show you the consequences it had. First of all, it had consequences for me because, as you've heard in the introduction, I had the honor of being awarded the Nobel Prize with two gentlemen here, W. Mernon and Eric Betzig, in 2014. And this comes, of course, with a very nice medal and followed by a banquet. I mean, pre-COVID time, banquets still took place. The last 2 years they couldn't. And now you're seeing what the laureates of last year were missing. Not only it comes with a fantastic banquet, but also with very good food and with very nice company. So this is something really, I must say, very, very memorable. But I'm not going to talk about that, of course. Obviously, I'm just showing you this to cheer you up. I'm going to show you how I got into my science. So how I got into this problem of overcoming the diffraction barrier. And the point that I'm making here, that usually as a scientist, of course, you of course you live a life, and so it's always connected with your personal life. And I just happened to have a look at Werner Heisenberg's book, autobiography book, and he starts out with the sentence, science is made by humans, full stop. And so in the end, there is always a human factor to the science that we are doing. Now, I was born actually, this is a map of Europe, as you will realize, in the western part of Romania, which was a communist country at that time, and but with German ethnic background. And so I convinced my parents at the age of 13 to leave the country and get out of the country because it was communist, and to go to West Germany. And so we managed, after many problems, wasn't easy, to go to West Germany. There was still the Iron Curtain at that time in 1978. And so to this town, which is actually famous for hosting a big chemical company, but that was not the reason why we went there. I liked the place because it was close to Heidelberg, and Heidelberg is a very old university town. And after I got my high school leaving certificate, I studied physics in Heidelberg, and like most physics students at that time, I was interested in doing working on basic problems, like working on, say, the unification of forces and particle things, particle physics, and so on. But at the time, I had to decide on what to choose as a subject for my master's thesis and finally for my PhD. And this is what I looked like as a PhD student back then, as quite different, as you will appreciate. I kind of lost courage because the students who were more advanced than me were saying, okay, don't do that, don't do theoretical physics because you're getting unemployed, and in the end you will end up as a taxi driver because there is no jobs in academia. You better do something that is applied, that gets you an education that you can find a job in industry. And so that had a lasting impression on me because, of course, my parents, having immigrated from Romania, still, of course, had to establish themselves socially and didn't have much money, obviously. And although, of course, education is free in Germany, it still was a responsibility. And so I signed up with a professor who set up a startup company, and a company that was a science company, so to speak, but still technological company, of course, that developed microscopes for the inspection of computer chips. And so, and to be specific, they developed so-called confocal microscope, laser scanning confocal microscopes for the inspection of computer chips. And I felt, okay, if I'm doing this, I may easily get a job because I'm doing something that is applied, because the customers of that company were companies like IBM and Hitachi and Siemens, and this company which developed memory chips at that time. And so actually my job was to inspect computer chips for these big companies, like IBM and so on. And now you can imagine that if you do this kind of thing, like just taking wafers for computer chips and inspect them with the microscope, this was not really science. I mean, this was technology, and I felt, why did I study physics if I'm ending up doing such technical things that are boring? And of course, microscopy was the subject of the physics subject of the 19th century, so totally outdated. There is no new physics in it. There was the resolution barrier. There's nothing you can do. I mean, I feel totally confined to something that was boring, and it became very miserable, to be honest, and very almost depressed, I would say, because I felt I should give up everything. I did the wrong decision in my life, and so on. And out of this misery, I thought maybe there's still something cool that I could do with this 19th century physics. And then I realized, oh, the only thing that is left and would be cool would be breaking the diffraction barrier. So something that everyone thinks that is impossible. If breaking the diffraction barrier would be something really cool to do. And so this kind of lifted me up, to be honest. This cheered me up because I felt now my, say, life is meaningful because I can work on a problem that no one works, because everyone thinks that this is impossible to do. And if that worked, this would be really groundbreaking. And so I started thinking whether there would be a way to overcome the barrier. I had all kinds of ideas that I dismissed. I must say, some, of course, in retrospect, were rather clever, but at the time the technology was not mature. And I looked into all kinds of things, quantum optics, because I was trained as a general physics person. I looked into all kinds of things. And I actually tried to convince my thesis advisor and other scientists in Heidelberg to give me the opportunity to work as a postdoc on this subject. But I said, oh no, this is no, not really what we should do, because everyone thought it is impossible. And so I was lucky that I met a person or two who were Finnish, from Finland, and they said, oh, why don't you come to Finland? There will be we can find some money that you can at least spend a year or two or so work on the problem. And so I went there. Of course, it was not a very rich lab, but it provided the opportunities. And about 8 weeks after I got there, with this idea in mind that there might be something, okay, that is worthwhile pursuing, there might be a way of breaking the diffraction barrier, I really got the idea that actually won me a share of the Nobel Prize many years later, of course. I'm exploring this, actually, 20 years later, yeah. And I'm explaining now to you how this works. And as I said, the problem was that all these molecules are emitting light because the green spot is so big that all the molecules fluoresce light and produce this confusion of fluorescent light here at the detector. And now I realized, being trained as a physicist, not only you can turn fluorescent molecule on so that they emit light, but you can also turn them off. The only thing you have to do, you have to use the right wavelengths of light. So what I did is I added another beam of light that is shifted in wavelength. So it's red light in this case. And if you use red light, so light in the emission spectrum of the fluorescent dye, to be precise, then you can turn it off, the molecule. You can make it dark, so to speak. So although it is flooded with green light. Now, of course, you don't want to turn off all the molecules. You want to turn off most of the molecules, maybe except the one in the middle. And this can be done if the red light is shaped to form a hole. You have to have a hole in the center, like a donut or whatever you want to call it. So you can, if you make a beam that has a hole, then of course you turn off all those molecules, except the one that is here, for example, conceptually. If you use the red shifted light, if you use the right wavelengths. And so that's what I realized. And if you turn these molecules off, of course, then the whole system behaves as though only that molecule would be emitting. Of course, they are all flooded with green light. You cannot avoid it. And there are many flooded with red light, of course. But in the end, the net outcome is that only one molecule is emitting light. And so the confusion that you usually have here at the detector is gone. And then you see signal only from this molecule, of course, and then you can take a picture, as I explained before, because then you move on to the next, you move on to the next, you move on to the next, and then you take a picture just by registering here the signal, displaying everything on a computer screen, and then you have a picture. And so I called it STET because this phenomenon of de-excitation is technically called in physics stimulated emission, but you don't have to worry about this term. The point I'm making here, so I published this together with an intern who visited me in Finland at that time, as a theoretical proposal that this should be viable, and I put in numbers showing that this must work and so on. And you might think now, I was about 30, 31, very young at that time, that the world said, oh, great, fantastic, a great idea. Somebody has had a great idea and can solve this big problem. It wasn't like this. I was going around advertising this idea. It was just a theoretical paper because I wanted to get money to do it in my lab. You know, I wanted to, and I even had my own lab. Didn't have my own lab. I wanted to have my own lab and pursue this development, but they didn't believe it. And I was going around applying to at least 30 places, and I lived in a very precarious way. So I just had fellowships. I gave licenses to companies because I patented the idea, gave licenses to companies, got money in return for research, yeah. And it was really, really weird. And I applied to the States for assistant professorships. And usually people say in the United States, people are more open to this. Yeah, but if you're not from an Ivy League school and nobody knows you and you don't have a good reference from in America, it's not so easy. And also America is not that open as one might think. So although there is an open culture in America, I don't want to play this down. But still, if you don't have the right pedigree, very hard. And so I didn't have the right pedigree, but there was somebody here at the Max Planck Institute, where I am now, actually, who, an American, by the way, he said, oh, he was a director at that time of this institute. He said, this is an interesting idea. Maybe it's right, maybe it's not right, but at least we should give him a try. And so I came here, and they give me a 5 years position to try it out. I applied for grants, initially rejected, believe it or not. Yeah, it was the funding agency said, no, this is not going to work, because the commission said it's not going to work, but eventually it worked. And to cut a long story short, this is now, say, a standard confocal resolution, and this is now the STAT resolution that is now roughly about an order of magnitude better. And so you can see now this 8-fold symmetry very nicely of these molecules. These are actually protein assemblies in a cell, so-called nuclear pore complex, nicely resolved here. And it's now in the German-speaking world, in Switzerland, Austria, and Germany, you find this image in textbooks in school, high school kids learn about these images and this technology, or you even find this is a cell biology book where I just happened to find it. Yeah, I bought it on Amazon and just happened to see it in the book. And although it's in the book, I still like making this comparison. You know, this is the standard resolution, you know, and this is the resolution that you get now. So I'm still, this is kind of childish, if you will. But anyway, so it was clear then that you can overcome the diffraction barrier. So as I said, and as you've heard in the nice introduction, this was the first concept. The idea actually, once you have an idea, of course, or an interesting research direction, you might be by yourself for some time, but then of course it spreads around the world and many others follow suit. And so the idea actually of doing something about the resolution also swapped over, so to speak, to the United States. And there was a man, Eric Betzig, who looked at my work, and he wrote me an email actually about that, and then basically checked out if I had left something. So if there's maybe something that I had left over, and actually found a variant. It's basically, if you think as from a physicist viewpoint, it's basically the same concept, yeah, but implemented in a fundamentally different way. And instead of using beams of light to turn molecules off, the turning on and off of the molecules is done on an individual molecule basis. And so here individual molecules are turned on and off. So there is a mechanism that allows the molecule to be flipped on. Such mechanisms were also used in this concept, but I'm not going into the details. And there is advantage of turning individual molecules on and off, because if you do that individually, then you have them already separated, so to speak. But of course, you need to find out where they are. That's the disadvantage of this method, and I will come back to this in a second. So this method called PALM, or some people call it STORM, also became quite popular and also achieved a substantial increase in spatial resolution, also by a factor of 10. But the point I'm making here is that both methods, both the STAT method and also the PALM method, they can, in theory, at least in theory, achieve a spatial resolution that is 1 nanometer. But at the time the Nobel Prize was given, it was not 1 nanometer, it was 20 nanometers, 30 nanometers, yeah, but not 1 nanometer. So it was clear the diffraction barrier is overcome, and both concepts could, in principle, get a resolution that is at the size of the molecule, which is about 1 nanometer. But none of these Nobel Prize winning methods could do it, actually. So there were only 20. Because maybe the Nobel Committee thought, okay, factor of 10 is enough for giving the Nobel Prize, and maybe it doesn't get better than that. So I don't know, but they thought, I have no idea. So the resolution in practice at the time the prize was given was 20 nanometers, and it was not possible, with a few exceptions, perhaps. There were some exceptions with that, some exceptions with Palm, but not as a general rule. And so the recent goal in my lab after the prize was to get the resolution down to the size of the molecule, down to about 1 nanometer. And what I realized is that you can do that if you combine the strengths of the two methods, STET and Palm-Storm. And without going too much into the details, the strengths of Palm, as I mentioned, is that you turn molecules on and off individually as individual entities, and then you assemble the picture later. And the strengths of STET is that you determine actually where the molecules are on and off, because you have a donut beam that really determines the position where the molecules are. You can relate the position of the molecules. You can always relate with the position of the donut, because the donut position is very well controlled and very precise. So this idea of injecting a coordinate with donut illumination is very, very powerful. And so I realized if you combine the two, the single molecule identification with this, say, donut making of the coordinates, you should get a very high spatial resolution. And so I introduced a new concept called min-flux. And the idea is that you turn molecules on and off individual, like here, but you use a donut beam like here, like instead. And then you find it out just by making sure that this center of this donut coincides with the position of the molecule. Now, the donut is not used to turn molecules off, because the on and off is done on a single molecule basis. What happens actually is that you make the green light, so to speak, the whole of the green light overlap with the center, and this combination of single molecules with this holy beam is very powerful to find out where the molecules are, and also have a perfect separation of individual molecules. And therefore, molecules that were that close, 11 nanometers, this is now a cartoon, could not be separated with the Nobel Prize winning method Palm or Storm, or if you want to call it like that. But this new method, min-flux, of course, could. So you see, because you find out the position of molecules with much higher precision, down to the 1, 2, 3 nanometer level. And so now the resolution is there, which is not there here. With the same number of photons, you get a much clearer picture. And I'm going to show again these nuclear pores. You've seen with that before, but now at much higher spatial resolution. Yeah, here they are very clearly, you can associate basically each little blob with individual fluorophores here, and therefore with individual proteins. But don't forget, you're not seeing the proteins, you're always seeing the fluorophores. But it's very clear now that the resolution is about 10 times better than with that. Yeah, very clear. So it's clearly better, and 100 times better than confocal with the standard. Yeah. So this would be a sort of Abbe's diffraction barrier. This would be the Nobel Prize winning method, STET, 10 times better. And we have now another factor of 10. And so we are about 100 times better than what people thought 20 years back would be the end of the story. Now, you've heard it, in order to disseminate the technology, I learned that the best thing is not just to license out to companies, because big companies, they tend to be slow. They want to sell their stuff that they have always produced. They have big hurdles for investing in new technology. And so I decided with my students, so with 7 of my former postdocs and PhD students, we decided to take the risk and set up a company that developed high-end microscopes. That's what we did, actually. And so I have to make the disclaimer here, because I own shares, of course, and I don't want to advertise this to you. I just want to say that this is not just technology that works in a lab. This is something that can also be used. Yeah, it can also be used in a lab, you put in a lab, it works, people push the button and get pictures. And this is indeed the case. So this is done with a commercial system, and there's many systems now in top places in the US, top places in China, top places in Europe. And I'm going to show you some applications which have been done actually by these three ladies who are scientists in the Max Planck Institute, actually. So Elisa has her own science group. And so this is so-called PSD95. That's a protein recorded with MinFlux in 3D. So you see, these are probably the sharpest ever pictures, sharpest pictures ever taken of this so-called PSD with focused light. Or here, this is a distribution of proteins in an axon. Initially, I should say this was seen with storm by Xiaowei Zhuang at Harvard University, and people didn't believe it. The critic said this is not true because we haven't seen this with electron microscopy, so it's not true. But we confirmed that both with that and now with 3D MinFlux, we have the sharpest picture ever of these structures that you cannot see with the electron microscope because the electron microscope doesn't give the specificity of labeling. So that's important. It shows how important it is to see specifically something, yeah, not just the general structure. So I'm just showing this as an example to prove that it's not just a theory, but it also works. Okay, now this company is now all over the world. I'm not going to, headquarters are in Göttingen, and there is, of course, also in US and in China. But the point, what I'm saying here is, as a message, the fluorescence microscopy, has finally reached the molecule scale optical resolution. So it's a message that is for me. It's still, although I have quite contributions to this field, quite substantial. I remember when I started out with this field in the late 90s, I gave a talk in Heidelberg. I was postdoc, sort of just a young group leader at that time, without permanent job, like an assistant professor without tenure. And then my thesis advisor, who of course I was not in his lab anymore, but he came to me saying, you should stop claiming that you can overcome this resolution barrier because you will never get a job in academia. You will never get a job. This is not good. You should stop claiming such things. You know, I didn't stop, and now we are 100 times better. You know, this is something, an interesting story, perhaps. So applications, of course, in the end, is it useful? Yes. Mapping biomolecules, mapping biomolecular dynamics. I can also see other fields, pathology, drug discovery. I think this will have impact. I'm 100% sure, because if a factor of 10 makes a difference, but a factor of 100 makes a big difference. So since this is a general talk, I would like to give you some things that maybe are useful. If you encounter similar situations in your own personal life and your life as a scientist, among the lessons I learned is that consensus does not always equate reality. So if there's a consensus in a field, it doesn't mean it's true. It applies also to other fields, of course, but the consensus can be wrong. I'm just telling you. So don't be worried if there is a consensus that is different from your own view. So that's one thing. But keep in mind, challenging this consensus is usually not welcome. That's part of the equation, because if you challenge consensus, you're putting other people out of business. Of course, the microscopy companies at that time and the community, other scientists that worked in light microscopy, they didn't like this idea that I'm coming, saying I'm breaking the diffraction barrier. They didn't say, oh, great, fantastic, because it was clear that I would put them out of business, or their work would look very small in comparison to mine if they worked on lifetime imaging or I don't know what, yeah, and I would break the diffraction barrier. And so that is clearly something that you have to keep in mind. Then another thing, curiosity, and I was just curious about it. I didn't want to do it just for helping the life science. I was curious whether this barrier could be broken, yeah. Curiosity leads to breakthroughs, and breakthroughs usually lead to economic value. So in the end, as I said, there is a company and there's 100 people who have jobs, very well-paid jobs, because they produce these microscopes. So curiosity usually leads to breakthroughs and also to values. And some people ask me, do you have like a motto or something? And this is the motto and the message I will give you at the end. Aim high, stay grounded. And with that, of course, thank you very much for listening so patiently. Thank you.
Okay, so thank you, Professor Hell, for the very inspiring talk. So I was inspired by your brave journey, actually. So I think the students here would really be inspired. And so if you have any questions, please leave your questions on the Q&A. And because we're using a webinar platform, you can't turn on your videos by yourself. But if you type video, we will turn on your video so that you can ask your questions directly. Okay. So I think Seungjun has a question. Okay, so I'll just read it out loud for the audience. In the picture of a protein, was the color red, green colored after photography, or did itself look in that color?
Yeah.
So
it's actually what we detect is fluorescent light. Yeah, it's not the protein itself, but it's the fluorophore that is attached to the protein. And the fluorophore has colors, yes, and it has different colors. But that, for example, there was a red fluorophore and there was a green fluorophore. Yeah. But the representation in the picture is not necessarily exactly that color, because it doesn't make sense. Yeah, so basically the different color represents different types of fluorescence light, so different wavelengths of fluorescence light. But the green and the red need not to be taken literally. Yeah.
So I think that's answered the question. Okay, so the next question. Thank you for the inspirational speech. Was there any advisors or helpers who supported your idea? What do you think the most important thing you need to overcome such circumstances?
Yeah, there were few. There were some who said, okay, we're going to support you. As I said, here in Göttingen, I had somebody who helped me to get the job. And some, of course, in Finland, of course, they said, okay, come here. But usually it's not that they believed as strongly as I did in the idea. They said, okay, this is an interesting subject, an interesting person, perhaps let's give this person a chance. There was skepticism. There was even skepticism in my own lab, I must admit. So when I had set up my little lab, there were students who said, yeah, but we should work also on other things, not just in resolution, because if we just work on this resolution thing, we may not get postdoc jobs, or we may not get jobs. We should also work on other things, because the community was not so open to this. And I had people applying to my place, and I said, okay, I would give you a subject to work on the resolution. I said, no, I don't want to work on resolution. I want to do other things, because people got jobs with other things, not with resolution, because they felt that it's not worthwhile working on the resolution because it won't work anyway. And so I had to have good faith. Yeah, I had to have faith in believing. I had to believe that this will work in the end, because so you in such case you always have to have at least one person who really believes in it and takes the lead, because otherwise it's not getting to the point. So it was. Yes, there were some people, of course, who supported me and said, it's interesting, you should do it. But still there has to be one person who's saying, okay, I go for it. So if you have an idea that you really believe in, you're convinced, you have to be convinced yourself. You should not wait others telling you that you should do it.
Okay, thank you for the very inspiring answer. So scientists have to be very brave. Yeah, believe in yourself. Okay, so Emilio has another question. What if the molecule we want to look at is bigger than the donut area? Does this impact the resulting image?
It's a very good question. So the donut area itself is always limited by diffraction. What I've actually shown is the area that where the molecules are turned off, okay, and also in the min flux case. So basically, where there is some light, yeah, you can say that it's not a 0 point. So the key is that you kind of confine the action to the 0 point. And it's a good question to ask, what happens if the 0 point, which is never a point, but a small area, gets smaller than the molecule itself? Yes, this can happen. And in that case, what happens actually is that the molecule behaves differently. You can say, a physicist would say, or a physical chemist would say, the dipole approximation of the light molecule interaction breaks down because the light field that is, so to speak, made by the donut is not constant over the molecule. It's changing over the extent of the molecule. Then the molecule behaves slightly differently in terms of the emission or the light molecule interaction. That could be even used to some extent to learn something about the size of the molecule or the extent of the molecule. It's something that one might think of. So I personally didn't think that is an interesting research field, because but it might be an interesting field. But yes, at some point, of course, the size of the molecule itself matters. That's correct.
Okay. Thank you very much for the answer. So I think a lot of people, you mentioned about this, but there's a lot of curiosity about, when did you really realize that this field is your passion?
Actually, I realized it when I realized that it's an interesting question. And I also enjoyed, I must admit, that I worked on a problem that everyone thinks wouldn't work. There is some advantage to that, because if you work in a field that hundreds of people work in, then you are in a huge competition, and you have to be better than 100 other people, and you might not be lucky. Yeah, you might be better, then you might not be lucky. And it's very, very hard. But if you work in a field that no one works in, then there's a lot of room for you. You can have the wrong idea, but it doesn't matter. Yeah, and then you do another one. So what I'm saying is there's a big advantage in doing something that no one else does. And so usually I encourage people to think about completely new problems, yeah, and work on subjects that no one works on, ideally. Of course, they should be useful. Yeah, but that was not my motivation. So at the time I worked on the problem, I didn't think of its use, so to speak. And honestly, I showed a motivational slide with the usefulness of light microscopy, but that was not my motivation. I showed that slide only to get money, yeah, for my research. That was the main purpose why I showed that, like a motivational talk. But my real motivation was to find out whether I can solve the problem. That was my motivation, nothing else.
Thank you very much. So the next question by Yundong. So what will be followed to convince people of the truth of the acquired result in the most accurate quality that has never been observed before? So if it's the first observation, if they have.
Yeah, it's a good question, because when we had the first pictures, people say, we don't believe it. Or some people said, it's a fluke. Yeah, it's just coincidence. Yeah, and it's not reproducible. There are even people who oppose the development. And so to tell you the truth, so when I had the first experiment showing that it'll work, I submitted it to Nature, the journal Nature. They didn't even send it out for review. They said no. Then I wrote it for Science. I sent it to Science, and they didn't send it out for review. I called up the editor and explained to him, this may revolutionize light microscopy. It's the first evidence that you can fundamentally overcome the diffraction barrier. And this is no. And they rejected it. They didn't even send it out for review. And then it was published in PNAS, because there was somebody as a reviewer who had met at the meeting and explained to him how it works. And so he knew from my personal discussion, how it works. And then he realized that I'm a trustworthy person then reviewed it by coincidence. He got to this reviewer, yeah, and then he accepted it and came out. And then they had better evidences later on. I sent it to Physical Review Letters. They published it in the end, but then Nature read this Physical Review Letters paper, and they invited somebody to comment on it, to write a news and views. And that person, basically, it's all archive publication in Nature in 2002. You find an article in 2002 in Nature that is saying that basically I'm cheating. So in nice words, it's saying in nice words that I'm cheating. You look it up, Nature in 2002, by a man called Ernst Selzer. And of course this had impact. So of course there is a lot of work that you had to do in order to convince the world, and it takes time, and you have to have courage. And in that case, of course, it helps having a permanent job. So afterwards, I got a permanent job. So I had, of course, the depth and the breadth to go for it. So in the end, of course, it's important after a certain period of time that institutions realize that if somebody works an interesting problem, the person should be given a tenure job or something, some safety to be able to work on it.
Okay, thank you for the very good answer. And Professor Rod Rolfe has a question. So this level of position measurement might find use in measurements in solid mechanics and or fluid mechanics with parameters such as stress in solid mechanics to measure extremely small values of displacement and thus strain. That is to measure the strain field at remarkably fine level of spatial resolution. Has this already been done, perchance?
The answer is not that I know of. Keep in mind, you have to have fluorophores. So it's all on fluorophores, yes. If you have threads and molecules, then you can see very small levels of changes. Particularly, I think the last minute I showed will have big impact in molecular dynamics. If you want to see proteins moving very quickly or at small scales, that there is a huge potential there, because there's no other method that could see such small displacements at this speed and with this hyper specificity, so to speak. In solid mechanics and in a strain field and so on, I'm not aware of anything. Of course, you can imagine having fluorophores, for example, in glasses or plastics or something, and then concentrate on individual fluorophores and see how they change on the nanometer scale if you put strain or something. Yeah, I can imagine that this works, yes. But I'm not aware of anyone having done that, yes.
Okay. Thank you for the very kind question. So we're running out of time, but could you perhaps have time for maybe one or two more questions? Okay, if so, then back then you worked on something that science community did not have faith in, yet your work illuminated the field of super resolution microscopy. There must be a lot of people who also fought against the ideas of the consensus, but I don't think many managed to turn out to be as successful as you. Personally, how lucky do you think you are as a person?
Yeah, the question is, how much is luck, how much is effort, and how much is skill, if you want. It has to come together. Was I lucky? In one way, I was lucky, and I tell you where I was lucky. So as I said, when I looked into the problem of overcoming the diffraction barrier, I did it just for the sake of doing it, for doing solving a great physics problem. But I had not realized at that time, although I knew that it's important for biology, I didn't know how important it really is for biology. And so after I worked for many years and got high resolution, I realized later or during the process that solving this problem is much more important than I thought initially. Because then I realized, oh my goodness, basically all cell biologists use fluorescent microscopes. I hadn't realized that before. So in that sense, I was lucky that I really happened to like to work on a problem that turned out to be important without me doing something for it, you know. So I was lucky that I happened to like something that turned out to be useful. That was not my accomplishment. My accomplishment was to work on a problem that people thought would not be solvable, and I found a solution eventually. But I didn't do much for the whole field being important, you know. In that sense, I was lucky.
Okay, so I think that's a very humble answer. So the next question is actually related to that a little bit. So people expert in developing techniques often struggle with the problem of finding an attractive application, even if the technique is sound. Do you have any tips for such people?
Application, yeah, it's a good question. Applications for a technique are obvious and can be easily done if the people who want this application to be done have a genuine interest. So applications work well if there's a genuine interest on both sides. If it's just for the sake of application, it's not going to work well. So I think the key thing is that there is this applies to all collaboration. There's a genuine interest on both sides, and both sides are ready to invest time and effort and all the rest of it.
Okay, thank you so much. And so we're really running out of time, but the questions are really just popping up. So maybe I think I can ask the last question for like the undergraduate students. So as an undergraduate student, what do I have to do or prepare to be a better scientist in the future?
Yeah, it's a very good question. I think you have to find out yourself what you want to do or what you like, because in the end, you're very good at things at which you really like, and it takes passion to do something of note. It really takes passion, and if you're passionate about something, then you're ready to go the extra mile, then you're ready to overcome difficulties. You know, as I said, when I worked as a more or less freelance scientist in Finland, Finland is very in the north, and winter it's not only cold, it's dark and depressive and so on. But I like to work on the problem, you know, so I could overcome these dark times because I liked it. And so this is really key, that you find out what you really want to do and what you really like to do. And if it's not science, it's not science. I mean, there's many other things that you want to do, yeah, or that you like to do in the end. So just find out what you want to do. And if it's science, good. If it's not science, also good. Yeah, because just do the things that you really want to do.
Okay. Thank you so much for the kind answer, and really thank you for all the kind answers, although we're out of time. And again, I'd like to apologize for the technical issues at the beginning.
No problem.
And we would really like to have you here on campus. So next time, maybe you can visit us in Ulsan, in UNIST. Okay.
Yeah, so thank you. Thank you so much. Actually, anecdote. So there was I visited South Korea many years back, and I was not very famous at that time. And my host at that time said to me, "We have to invite you now, because you never know, in 10 years it might be harder." And I asked, well, what is he saying? Yeah. But I still recall this thing. This was in about 2002 or 2003, very early. So when I still struggled to convince people that this would work, this person in Korea actually realized what was going on.
Mm-hmm. So okay. You really have to visit us.
Yeah.
Okay. So thank you so much once again, and really looking forward to seeing you in person in the near future.
Yeah. Thank you. All the best. Mm-hmm. Thanks for listening.
Okay. Thank you for the very inspiring talk. Bye-bye.
Bye.